There are two common methods to display a molecule: Wedge-dot and Fischer. But how do we convert between them? Here is a molecule depicted in Wedge-dot. Let's take our eye and imagine looking down the central carbon-carbon bond in red and blue. If you place your eye in that location on the paper or screen, it may help you imagine whether the substituents going back or forward from the plane are now to the left or right of your eye. What do we see in terms of a Newman projection? Is the red carbons, that's to say the carbon nearest the eyes, hydroxyl, to the right or left? Well, in Wedge-dot, it's coming out of the plane towards us, and with your eye in that position, it's to the right of the eye. Thus, it's depicted to the right of the red dot in the Newman projection form. What about the hydroxyl attached to the blue carbon, the carbon further from the eye? It's on the same side, which we previously agreed is on the right side. So in the Newman projection, it is attached to the blue circle on the right side. Now we will rotate that central carbon-carbon bond, with the nearer red carbon moving through 180 degrees, with the primary alcohols going from anti-staggered to syn-eclipsed. The Fischer projection must come from this syn-eclipsed orientation with the terminal carbons. The nearer carbons, red hydroxyl, is on the left, whilst the further carbons, blue hydroxyl, remains unmoved on the right. We now view the molecule from the opposite side to the terminal carbons. This is what we see. But we drop the dashed and bold nomenclature for out and into the plane of paper or screen, as this is assumed in the Fischer projection. In 1900, Fischer and Rossinoff, based on the Fischer projection, developed descriptors to indicate the sense of stereochemistry at the stereogenic center furthest from the highest priority carbon: aldehyde with carbohydrates and carboxylic acid with amino acids, except for isoleucine and threonine. Initially, plus glyceraldehyde was guessed to have the hydroxyl group on the right. The luck of this guess was only demonstrated 50 years later with X-ray crystallography studies that provided proof. This is the open form acyclic ribose. We can assign each stereogenic center with a Carn-Ingold-Prelog CIP descriptor. In this case, they are all R. We rotate the third carbon, where the carbonyl carbon's the first carbon, by 180 degrees. Neither the second nor the fourth carbon are rotated. The backbone of carbons curves back on itself and no longer forms a zigzag. Now we look down what we're calling the top of the molecule from the highest priority carbon, carbonyl. Here, an aldehyde carbon. The second carbon's hydroxyl is to the right from the eye's view, and all the other stereogenic centers, carbons, hydroxyls, are on the same side. Thus, in the Fischer projection depiction, the hydroxyls are all on the right. All horizontal bonds face towards the viewer, whilst all vertical bonds generally face away from and never towards the viewer. Even the central vertical bonds depicted here as single lines, not dashed lines. All hydrogens directly attached to the key carbon backbone are always displayed. This is the formal Fischer projection. Now we focus on the second to last carbon in carbohydrates, or last bottom stereogenic center, excluding isoleucine and threonine, where it is the second to last. Is the higher priority group of the last stereogenic center, so hydroxyl with carbohydrates and amine with amino acids, to the right or left? Here, the hydroxyl is on the right. From the Latin Dexter on the right and Laevus on the left, we describe this ribose as being capital D. Ribose informs us of the stereochemistry of the other stereogenic centers relative to this one. So, let's reflect upon the enantiomer of D-ribose. First, let's provide the Carn-Ingold-Prelog CIP descriptors for all the stereogenic centers. In this case, they are all S. Now we will depict the molecule in Fischer projection, with the highest priority carbon, a carbonyl, at the top, facing back into the screen. We look at the second to last carbon in carbohydrates, or last stereogenic center, except second to last stereogenic center in the case of isoleucine or threonine, here. So, is the highest priority group hydroxyl for carbohydrate and amine for amino acid to the right or left? In this case, the hydroxyl is to the left, thus Laevus, abbreviated to capital L. This again is the formal Fischer projection.